right, today we want to see how we can come up with the velocity relation to matrix relation through matrix exponential. Let me explain. So let's say we have a rigid body, and then we have a vector connecting 2 points in that rigid body. So it is a fixed vector in that rigid body. So let's say we have a coordinate system. Let's call it B, for attached to the body of that rigid body. Then let's say we have a fixed coordinate system. And let's call it A. Then we know from the dynamics that the rate of change of that R in the coordinate system A, because in coordinate system B, R is not changing anyway, because it is fixed to that rigid body. And a coordinate system, an observer that it is attached, welded, fixed to that rigid body, doesn't see any change in R. It always see R in a constant position relative to that rigid body. So R dots, change in coordinate system A, equals to omega cross R. And that omega is angular velocity of the rigid body. Let's say omega equals to omega 1, omega 2, omega 3. It is a vector that describes the angular velocity of the rigid body. In other words, angular velocity of the coordinate system B with respect to A. So we know that ultimately, when we measure R at coordinate system A, it would be some rotation matrix. Originally, let's say coordinate system was, we call it R0 in coordinate system A. Everything is in A. So R0 is those numbers that explain that R in A. Then when we multiply it by R, that rotation matrix, it gives us, after sometimes it gives us that numbers in coordinate system A again. So we can go from this to this. How come the rate of change of that R, then this relation, that it is a matrix relation, rotation matrix times that, becomes a vector notation. Vector, I mean, multiplication, cross product. So there is another video on that, and you can see explanation in textbook as well. This time we want to go the other way around, from this to this, which is not well discussed in a lot of textbooks. So we want to see if we have this relation, the rate of change is that, how come after some time we can say that, okay, the final value equals to rotation matrix times R0. So let's start from that cross product. Cross product, if R is X, Y, Z, let's say R is X, Y, Z, then omega cross R, in order to calculate that, one way is to write it this way, I, J, K, right? And then put omega 1, omega 2, omega 3 here, and X, Y, Z here. All right, and that's, we can write it this way. We get rid of I here. We would have omega 2Z minus omega 3Y. Then for J, we would have omega 3X minus omega 1Z. And then for K, we would have omega 1Y minus omega 2X. For any cross product, in fact, we can do it in matrix multiplication by defining an anti-symmetric matrix. So negative, it would be 0 on the diagonal. Then we would put negative omega 3 here, omega 2 here, then negative omega 1 here, and this is 0, and this is 0. Then we put omega 3 here, negative omega 1 here, and negative omega 2 here. So instead of doing this cross product for any omega, any vector for that matter, we can have this anti-symmetric matrix, and let's call it M. And when we multiply it by X, Y, Z, we will see that we would have this negative omega 3y plus omega 2z, which is that one. Then this gives us this one. So we can, instead doing it with matrix multiplication. So when we have our dots, so now that our dots equals to, I mean, it is, if I don't put a vector sign, if this equals to MR, there is a video that we can show that there is a video that I have in my channel when we have this relation, similar to one-dimensional case, that when we have y dot equals to ay and y of 0, let's say at time 0 is y0, then we can say that y equals to e to the power of a t y0. Because the derivative of that, a comes out and down. And at time 0, this becomes 1, so y0. So the same thing would be for matrix multiplication. Again, there is another video on that. Because we define this e to the power of at as a series, we can define the same series. You see, this is 1 plus at plus at to the power of 2 over 2 factorial plus at to the power of 3 factorial. The same thing, we can put matrices here. And we call I plus mt plus mt to the power of 2 over 2 factorial. And matrix to the power is well defined. So we can show that the derivative would be the same thing as when we have that, we would say R equals to e to the power of mt R0. Now, you see, we are getting close, but we have to show that this e to the power of mt is a rotation matrix. This is anti-symmetric matrix. You want to show that this is a rotation matrix. Again, there are other videos in my channel, and also you can look up online, that when M can be diagonalized by two other matrices, let's say U inverse, this is diagonalized. So this is just a diagonal matrix, or block diagonal matrix. Then e to the power of m, it is the same as, I just keep these, e to the power of dt. And then e to the power of diagonal matrix is easy to follow. Now let's analyze this one. This is anti-symmetric matrix. What are the eigenvalues of this? In order to make this diagonalize, we have to look at the eigenvalues and eigenvectors. But let's see, what are the eigenvalues of this? If you see, this should be the same as that omega cross R, right? This multiplied by R, this matrix should be the same as that cross product. So this times vector omega is the same as omega cross omega, which is 0. Any vector cross itself is 0. So this cross this times omega should be 0. So that omega is eigenvector for eigenvalues of 0, because that m, that vector omega, equals to 0 omega. We know that that is an eigenvector, and the eigen corresponding eigenvalue is 0. The other two eigenvectors are complex. We can show that, I mean, I will show that in MATLAB because it is easier to do manipulation in MATLAB. Toward the end of this video. All right, so the eigenvalue of this matrix, this antisymmetric matrix, it has three eigenvalues. One of them is real. We saw that, okay, omega should be eigenvector with eigenvalue 0. The other two are complex, and they are plus minus I omega. And what is this omega? That is the magnitude of that vector omega, which is omega 1 square plus omega 2 square plus omega 3 square root of that. So we have these two. Then when we make this into a block matrix, so this M, if we do it into a block matrix, we can find U inverse. We can find U such that U inverse du becomes M. So this is M. And then this D would look like this. 0 omega negative omega 0. This is that block representing these two complex values, but it is not complex anymore. And then we would have 0, 0. Then this is the last eigenvalue, which is 0. So the eigenvalues are in this block and this one, because the real part is 0, so we would have 0 here. Again, when we have complex eigenvalues, we can make it into a block diagonal matrix. There is a video on my channel explaining how to do that. Then this, if you think about this, this is like rotation matrix in 2D for 90 degrees. Because if you think about it, I mean, if I factor out omega, I can write it as omega. So let's say D equals to omega, then we can put this 1 and negative 1. And this is a rotation matrix by 90 degrees in 2D, right? Because this 1, 0 would go to 0, 1. So this is I, which is rotated 90 degrees, which becomes J. And this is J, which is rotated 90 degrees. So the reason that I'm saying that is that after 4, I mean, this to the power of 4 would go back to I, and then to the power of 5, it would be again the same. So we have a repetition. So calculating this is easy. So we do that in MATLAB. The rest of it is in MATLAB. All right, let's do that in MATLAB. All right, so this is that in MATLAB live script. This is version 2023A. So we define omega, I mean symbolic omega, and symbolic R. So vector omega cross R would be this. If we, based on that omega, we make an antisymmetric matrix this way, like the one that we did on the glass board, then M times R would be the same as omega cross R. Then when we do the eigenvalues, we see that the eigenvalues are complex and eigenvectors are complex conjugates. So we would have two eigenvectors that are complex conjugates, and we have two eigenvalues, three eigenvalues. So this one is real, this one is, these two are complex conjugates. You see, omega 1 is omega 2, I mean, this sigma 1, I mean, MATLAB symbolic toolbox makes some summarization. So it is negative omega squared. This is, in fact, omega squared. So negative omega squared, or square root of that. So In other words, it is plus minus I omega, and omega would be the magnitude of omega. And these are the eigenvalues. You see, it is negative, positive I omega and negative I omega, and this is 0. So the eigenvalues, MATLAB put them on diagonal of a matrix V here. So I rearranged those just to see that clearly and multiply it by denominator. So it wouldn't look like this. Then you will see that clearly here that one of the eigenvectors corresponding to 0, I rearranged the eigenvectors. It is corresponding to 0 eigenvalue. It is omega 1, omega 2, omega 3. And these two are complex conjugates, right? The real parts are the same. The imaginary part, which is the part with sigma 1, it is negative here, positive here, negative here. So we stack these eigenvalues. The real part, the real part would be this, this, and this, and imaginary part, but without the I, it would be this, this, and 0. So we stack the eigenvalue, eigenvectors, you like that, you see, the real part, and that imaginary part without the I. So the eigenvectors are, let's say it is V plus IY. So this is V and this is Y. And this is the other eigenvector. Then if we do this U inverse MU, so this M is that antisymmetric matrix. If we multiply it by U inverse and U, then we would have block diagonal matrix, which is A star here. That block diagonal, it has 0 on the diagonal, and this is negative omega, and this is positive omega. So let this be omega. Then we will have this. We want to find the exponential of this. So we would find the power 1 of that, power 0, power 1. We factor out omega. Then we find power 0, which is just I, power 1, the same thing, negative 1, power 2, power 3, and power 4, you see, it is I, because it is like rotation around, if we factor out omega, this would be a rotation around z-axis for the x. So after 4 iteration, we would go to I. Power 5, it would be the same thing. So this helps us to find e to the power of mt. Again, this is my m. So mt, we would have t to that. We want to find power 1 of this, power 2 of this, over 2 factorial, and so on and so forth. So you see here, we want power 2 of power 0 of that, power 2, power 1, power 2, power 3, and then we want to add them all together, power 4. And we see that if we add them all together, we get something like this, and sigma 1 is this one. Then if we compare it with Taylor series of sine, you see up to the third term, it is exactly the same. So this is Taylor series of sine omega t. And this is cosine omega t, that's sigma 1, which is here. So in fact, we would have negative sine omega t, cosine omega t, cosine omega t. We can do it even with MATLAB, simplify. I mean, this is matrix exponential of that diagonalized t. So that M matrix is a rotation matrix. So we showed that this to the power of et becomes is this e to the power of this t. So in other words, e to the power of dt is a rotation matrix, omega t, cosine omega t, negative sine omega t, sine omega t, cosine omega t, and 0, 0, 1, and 0, 0. So this would be a rotation matrix. How about these two? This is like change of coordinate. What does that mean? We go from one set of coordinates and we does nothing to that vector. We just change those numbers into our new coordinate system. So we have a vector, so we change it, change the numbers, not the vector itself is constant in space. So we just look at the same vector in some other coordinate system. So we apply u on that vector. So we see this same vector with different numbers because the representation of the same vector in two different systems would be different. So we applied that. So it's like we have two spaces. All right. We go there from this space representation to there. Then we rotate it, and this is coming back. So it's like we have the same vector. We state that vector in the new coordinate system by applying this u. We rotate that vector by rotation matrix, which is this. And then we come back to our original coordinate system. All right, so this would be a rotation matrix this would be a rotation matrix because this is a rotation matrix. And this is just to change the coordinate back and forth to apply this rotation matrix. So this would be a rotation matrix like that, even though it wouldn't look like simple like cosine omega t, negative sine omega t, sine omega t, cosine omega t, 1, 0, 0, 0, 0. It wouldn't look like that in our coordinate system, but in fact, it is a rotation matrix in some other coordinate system. All right. So we went from here to here using matrix exponential. So that's why this cross is in fact derivative of that, because when we do integration of that, we get rotation matrix. All right. Thank you.